Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out some numerical examples on compound stresses. Let us start the first example. The state of stress in a two-dimensionally stressed body is shown in figure. Determine the principal planes, principal stresses, maximum shear stress and their planes. A body is subjected to plane state of stress. In x direction, compressive stress is acting. So the stress is acting towards the element. So in x direction, compressive stress is acting and its magnitude is 120 Newton per mm square. So sigma x is minus 120 Newton per mm square. In y direction also, the stress is compressive. The stress is acting towards the element. So in y direction, stress is minus 80, sigma y is minus 80 Newton per mm square. And on the right face, that is shear stress. Let us look at the right face. Right face, the shear stress is downward. So it is minus 60 Newton per mm square. So tau xy is minus 60 Newton per mm square. So you can always see the right face and top face. Right face stress is leftward. Leftward you can take negative. Normal stress is leftward. So sigma x is negative. Shear stress is downward. So shear stress is negative. On the top face, the normal stress is downward. Downward you can take negative. Now let us find out the principal planes. Principal planes you can find out using the expression tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. In this tau xy we know tau xy is minus 60, sigma x is minus 120 and sigma y is minus 80. Substituting that you get 2 into minus 60 divided by minus 120 minus of minus 80. So that will make plus 80 and you will get minus 120 divided by minus 40 or you will get plus 3. So that is tan 2 theta p value. You can solve for 2 theta p as 71.56 degree and from this you can get theta p1. So we will get theta p1 first solution for principal planes is 35.78 degree. So once you know theta p1, you can find out the other principal plane theta p2 by adding 90 degree to theta p1. So theta p2 is equal to theta p1 plus 90 degree or 125.78 degree. So you got the principal planes. Theta p1 is 35.78 degree and theta p2 is 125.78 degree. These angles are measured from the vertical in the counterclockwise direction. So from the vertical 35.78 degree. Okay, so that is one of the principal plane and perpendicular to that is an next principal plane. Now let us find out the principal stresses associated with these planes. So principal stresses formula is sigma 1 and sigma 2 is equal to sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. Now let us substitute the values of sigma x, sigma y and tau xy. Sigma x is minus 120 and sigma y is minus 80. Minus 120 minus 80 by 2 plus or minus 120 minus of minus 80 will make plus 80 by 2 square plus minus 60 square. So you will give minus 100 plus or minus root of minus 20 square plus minus 60 square. So that gives values minus 36.75 and minus 163.25 megapascal. So these are the principal stresses and you get two values. One value is 163.25 compressive and another value is 36.75 megapascal compressive. So these are the extreme values of normal stresses existing on the body, and maximum compressive stress is 163.25 and minimum value of compressive stress is 36.75 megapascal. These stresses will occur on principal planes, and any other plane you check, you will get stresses between these values. So you will not get stress more than 163.25 or less than 36.75 megapascal. Now let us find out the maximum shear stress. The maximum shear stress is given by plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. Let us substitute for sigma x, sigma y, tau xy. So it is equal to plus or minus 120 plus 80 by 2 square, minus of minus 80 will make plus minus 60 square. So that will give plus or minus 63.25 megapascal. So maximum shear stress is same on both the planes, plus or minus, and shear stress plus or minus doesn't have much significance, and both the planes will have shear stress 63.25 megapascal. Any other plane you take, shear stress will be less than this. So these maximum shear stresses occurs on planes of maximum shear stress. So we need to find out the planes of maximum shear stress. For finding out that, you can use the expression tan 2 theta s is equal to minus sigma x minus sigma y divided by 2 tau xy. Substituting the values, you get tan 2 theta s as minus 0.333. Now the value of 2 theta s is minus 18.43 and theta s is minus 9.215 degree. And we know there are two planes of maximum shear stress which are mutually perpendicular. So if you add 90 degree to this, you will get other plane of maximum shear stress. So theta s2 is equal to theta s1 plus 90 degree, which will give 80.78 degree. So these are the planes of maximum shear stress. On these planes you will have maximum shear stress. Minus indicates from the vertical you have to move in the clockwise direction. So one plane will come like this and perpendicular to that is other plane. So these are the planes of maximum shear stress. On these planes you will have that maximum shear stress which we have calculated. Now you can also find out the planes of maximum shear stress by just adding 45 degree to the principal planes, because principal planes and planes of maximum shear stress are separated by 45 degree. We already know that principal plane theta p1 plus 45 degree will give theta s1. So you can get one of the planes of maximum shear stress as 80.78. Another value theta s2 you get just adding 45 degree to theta p2 plus 45, which will give 170.78, which is equivalent to minus 9.2. 170.78 from the vertical in the anti-clockwise direction is equivalent to minus 9.22. So these are the same plane. So you are getting the same solution. Theta s1 and theta s2 can interchange. These are the two planes where maximum shear stress occurs. Or you can take theta s1 as theta p1 minus 45 degree, plus or minus 45 degree. From principal plane you can take plus or minus 45 degree to get the planes of maximum shear stress. Now let us work out another example. A plane element is subjected to stresses as shown in figure. Determine the principal planes, principal stresses, maximum shear stress and their planes. Sketch the planes. Similar problem, but finally you have to sketch the planes. That is, you got the principal planes and planes of maximum shear stress. You have to show these planes on a sketch. Now the stresses acting in x direction is plus 60 Newton per mm square, and y direction you have minus 40 Newton per mm square, and tau xy is plus 10. So sigma x is plus 60, because on right face you can see right word is plus, and sigma y on the top face it's downward, so minus 40 Newton per mm square. Shear stress is on right face it's upward, so plus 10 Newton per mm square. Now let us find out the principal planes. Tan 2 theta p is 2 tau xy divided by sigma x minus sigma y. So 2 into 10 divided by 60 minus 40 with plus 0.2. So 2 theta p is 11.3 degree, or theta p1 is half of this, 5.65 degree. Now you can find out the next principal plane, theta p2, by adding 90 degree to this. So theta p1 plus 90 degree will give 95.65 degree. So these are the principal planes where you will have principal stresses. Now principal stresses is given by sigma x plus sigma y by 2 plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. Substituting for sigma x and sigma x is 60, sigma y is minus 40, so 60 minus 40 by 2 plus or minus 60 minus 40 will make plus 60 plus 40 by 2 square plus 10 square, which will give 60.99 megapascal and minus 40.99 megapascal. These are the principal stresses. So one of the plane you will have maximum tensile stress, another plane you will have maximum compressive stress. So within this body, the maximum tensile stress will be 60.99 megapascal and maximum compressive stress will be 40.99 megapascal. If you take any other plane other than principal plane, you will get tensile stress less than 60.99 only, or compressive stress less than 40.99. You cannot get tensile stress more than this or compressive stress more than this. So these are the principal stresses. Now let us find out the maximum shear stress. Maximum shear stress is plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. You can also find out maximum shear stress using the equation sigma 1 minus sigma 2 by 2. You got the principal stresses. Sigma 1 minus sigma 2 by 2 will give the maximum shear stress. So 60.99 minus of minus 40.99 divided by 2, or you will get 50.99 megapascal. That will be the maximum shear stress. And let us find out using this formula. Tau max is equal to plus or minus root of sigma x minus sigma y by 2 square plus tau xy square. So plus or minus 60 minus 40 by 2 square plus 10 square. It will give plus or minus 50.99 megapascal. So you are getting the same result by using sigma 1 minus sigma 2 by 2. Planes of maximum shear stress you can find out by just adding 45 degree to the principal planes. Theta p1 plus 45 degree will give theta s1, and theta s2 is equal to theta p2 plus 45 degree, or just add 90 degree to the one of the planes of maximum shear stress. You got one of the planes of maximum shear stress, just add 90 degree to that. Since planes of maximum shear stresses are mutually perpendicular, you can add 90 degree to that, or from principal planes they are separated by 45 degree. Add theta p2 plus 45, which will give 140.65 degree. So these are the planes of maximum shear stress. So after getting principal planes, principal stresses, maximum shear stress and planes of maximum shear stress, you are asked to plot these planes on a sketch. So let us show these principal planes on the diagram. So from the vertical you should measure all the angles. So you got the first principal plane 5.65 degree, so that is theta p1. So from the vertical you take 5.65 degree, that is one of the principal plane. Perpendicular to that is another principal plane, that is 95.65 degree. So this is another principal plane. So these are the principal plane. I have marked it there, principal plane, that is shown in the red. The lines shown in the red are principal planes. Now the planes of maximum shear stress, it is 50.65 degree. So by adding 45 degree to this 45 degree to the one of the principal plane, so you get the first plane of maximum shear stress. So they are separated by 45 degree. This principal plane and planes of maximum shear stress are separated by 45 degree. So theta p1 plus 45 degree will give the first plane of maximum shear stress. Then you can add 90 degree to that, which will give the next planes of maximum shear stress. So 50.65 plus 90, 140.65, 140.65. So that is the another plane of maximum shear stress, and you can see that they are mutually perpendicular. These blue lines, they are planes of maximum shear stress, they are mutually perpendicular, and these red lines, they are principal planes, they are also mutually perpendicular, and all these adjacent planes are separated by 45 degree. Principal plane and planes of maximum shear stress, they are separated by 45 degree, and here also it's 45 degree, and this is 45 degree, and again 45, 45. Any two adjacent planes, that is principal plane and planes of maximum shear stress, are separated by 45 degree. So if you get one of the plane, you can find out all other plane. So if you get one of the principal plane as 5.65 degree, just add 45 will give the one of the planes of maximum shear stress. Add to this 90 degree, you will get the second principal plane. Add for this value, that is first planes of maximum shear stress, you add 90 degree, you get the other one. So I have shown the planes on the sketch. The red lines shows principal planes and blue lines shows planes of maximum shear stress. I have shown the angles also. All angles are marked from the vertical in the counterclockwise direction. Clockwise if you mark, it is negative. So this is planes of maximum shear stress minus of whatever angle it is there, that is 180, total 180 minus 140.65, so that will give 39.35. This angle is going to be minus 39.35 since it's measured from the vertical in the clockwise direction. So you can also specify this plane by minus 39.35 degree. Okay, so let us go to the next example. Show that in a two-dimensional stress field, the principal planes and planes of maximum shear stress are separated by 45 degree. So you have already seen that they are separated by 45 degree, and we have to show that in a two-dimensional stress field they are separated by 45 degree. In a general case, you should show that they are separated by 45 degree. So principal planes are given by tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y, and planes of maximum shear stress is given by tan 2 theta s is equal to minus sigma x minus sigma y divided by 2 tau xy. So tan of any angle represents the slope. So the product of these slopes of these two angles you can calculate. The product of slopes, that is tan 2 theta p into tan 2 theta s, you can calculate. So product of slopes, tan 2 theta p is 2 tau xy divided by sigma x minus sigma y, and tan 2 theta s is minus sigma x minus sigma y divided by 2 tau xy. As we know this is the reciprocal of this and with a minus sign, and they represent the slope, and the product of slopes you can calculate. The product of slopes you will get -1. So sigma x minus sigma y cancels, 2 tau xy cancels, get -1. So the planes 2 theta p and 2 theta s are mutually perpendicular. Since the product of slopes are -1, they are mutually perpendicular. 2 theta p plane and 2 theta s plane are mutually perpendicular. So that means they are separated by 90 degree. 2 theta p and 2 theta s are separated by 90 degree. So that means 2 theta p plus 90 degree is equal to 2 theta s, or dividing by 2, theta p plus 45 degree is equal to theta s. So therefore the planes, principal planes and planes of maximum shear stress are at 45 degree to each other. 2 theta p plus 90 degree is equal to 2 theta s. So that is the meaning of they are mutually perpendicular. So dividing by 2, you get theta p plus 45 degree is equal to theta s. So the principal planes and planes of maximum shear stress are separated by 45 degree. They are at 45 degree. So we have proved it in a general case. Let us go to the next example. Show that the sum of the normal stresses on any two mutually perpendicular planes is a constant. Sum of the normal stresses on any two mutually perpendicular planes is a constant. When a body is subjected to plane state of stress, we know the normal stress acting on a plane which is inclined theta from the vertical is given by sigma is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. And this is the normal stress acting on a plane inclined theta from the vertical. So I will represent it by sigma theta corresponding to theta plane. That is, when the inclination from the vertical is theta, this is the normal stress on that plane. Now let us consider another plane which is perpendicular to this. So this theta is arbitrarily taken. Theta can be say 10 degree or 20 degree or whatever it is. So on that plane you will get this normal stress. You just substitute for theta. Now let us take another plane which is perpendicular to that. Okay, so that means the angle will be theta plus 90 degree. So the normal stress on that plane will be, we will represent it by sigma theta plus 90. But the angle from the vertical is theta plus 90. Whatever that theta we have taken, 90 degree you add to that, that will give a perpendicular plane, and stress on that plane is the general formula I will apply. Substitute theta as theta plus 90. Okay, the angle has changed now, theta plus 90. So we will get this formula. Even theta here I have substituted as theta plus 90. So this will reduce. Cos 2 theta plus 180 you get, or cos 180 plus 2 theta. Cos 180 plus 2 theta is minus cos 2 theta. And here you get sin 2 theta plus 180 or sin 180 plus 2 theta. Sin 180 plus 2 theta is also minus sin 2 theta. So here you will get minus cos 2 theta, here you will get minus sin 2 theta. So 180 plus 2 theta and sin 180 plus 2 theta, that will give minus values. So sigma x plus sigma y by 2. So since this is minus sigma x minus sigma y by 2 cos 2 theta minus tau xy sin 2 theta. Now you can add first and second equation. First equation, here you have plus, okay, plus value, same terms with a plus sign. This sigma x plus sigma y by 2. So here also you have the same, but these two terms will get minus. Okay, so adding these two terms, this sigma theta plus 90, these terms will get cancelled. So sigma theta plus 90 will get sigma x plus sigma y by 2 plus sigma x plus sigma y by 2. So the second term and third term will get cancelled. You have plus values there for the first equation, and first equation also you have this term. This term is repeated twice while adding, so you get sigma x plus sigma y. So sigma theta plus 90, you will get sigma x plus sigma y. That is the normal stress applied in the x and y direction. Summation of the normal stresses applied on the element in the x and y direction. And that we know it is a constant for a given stress field. That is going to be constant. The applied stresses, the summation of the applied normal stresses is going to be a constant. So any two mutually perpendicular plane, if you sum up, that summation should be equal to sigma x plus sigma y, and that's going to be a constant. That is true for even principal stresses. Principal stresses are normal stresses on two mutually perpendicular planes or on principal planes, and principal planes, you know, they are mutually perpendicular. So even sigma 1 plus sigma 2 should be equal to sigma x plus sigma y. Any plane, okay, is for applicable for any plane. So you can even add normal stresses on principal planes, that is principal stresses. So sigma 1 and sigma 2 you can sum up, that also should give the value equal to sigma x plus sigma y. Hence we have proved that the summation of the normal stresses on any two mutually perpendicular planes is a constant irrespective of that angle theta. So arbitrarily you take any two mutually perpendicular planes, the summation of the normal stresses on those planes should be a constant. That's all for today. Thank you for watching.